Hello and welcome to this acids and bases dilution question, including a Ka calculation and the influence of partial neutralization on that particular calculation. Let's have a quick run through partial neutralization first. If we have an excess of weak acid added to a strong alkali such as sodium hydroxide, the hydroxide ions will completely neutralize an equal amount of hydrogen ions from the weak acid. The solution remaining behind after the reaction contains the excess weak acid plus the same number of moles of conjugate base as OH- you started with. So let's take HA as our weak acid. H plus will be the protons that are dissociated and A minus will be the conjugate base. So if we react that with 0.5 moles of OH minus, 0.5 moles of the original HA will remain unreacted. But the other half of the HA will react with OH minus fully to make A minus, or the sodium salt in this case if it's sodium hydroxide for example, and there'll be some unreacted HA left behind. This mixture is now called a buffer mixture. This video isn't about buffers, but it's useful just as a side point here. There are other videos I've done on buffers that delve into this a little bit more deeply. So let's look at this in a question. It describes a weak acid with its Ka value at the top and tells you about two different solutions that are put together, and then a mixture is formed once they react with each other. So a solution was formed by mixing 10.5 centimeters cubed of one solution and 25 centimeters cubed of another. So let's treat them differently. I've color-coded the actual solutions, and I'd like you to imagine that the two beakers were the two different solutions. So we haven't added them together yet. So let's calculate the number of moles of hydroxide as 0.084, and the number of moles of HX, the original weak acid, as 0.023. So you can see that the 0.023 is bigger than 0.0084. So now we can work out the moles of HX left behind. So the simple way to do this is to work out the difference between them, and that gives us 0.0146. So now we can work out the concentration of the remaining HX. Now remembering that the two solutions have been mixed together, you now have a new total volume of 35.5. So C equals N over V, which is our 0.0146 over 0.0355, which gives us 0.411 ... So that's a rather long number, which I've truncated here, but I've kept the original in my calculator. I can do the same for X minus, but let's have a quick look at this for a moment. We have 0.0084 moles of NaOH. That's going to react completely with an equivalent amount of HX to make 0.0084 moles of NaX. So why is this suddenly important? If you remember an original weak acid, you assume that NH plus equals NX minus. But what's happened here is you've made some extra X minus because some of the acid has been completely neutralized by the NaOH. In other words, a partial neutralization has occurred. So you have to take this extra X minus that's now in the mixture into account because H plus and X minus are no longer equimolar. So let's do the concentration of X minus first. Doing the same things we did before, 0.0084 over 0.0355 gives us 0.2366 ... Again, a long number which I'm going to keep in my calculator memory. Now I need to work out the H plus ion concentration of the remaining solution. So looking at the Ka expression, usually we'd rearrange that and we'd make H plus times X minus into H plus squared. Because they're different this time, we can't do that, so we've got to rearrange in a slightly different way. So remembering the two long numbers we had before, we divide one by the other and multiply that by the Ka value to give us 9.125 times 10 to the minus 5. So we can now sub that into the pH expression and get 4.04, remembering that pH values are always expressed to two decimal places. Okay, hopefully this has been a quick and useful look at this type of more challenging example. Until next time, thanks for listening, and see you soon.